Hello everyone. In this video, we are going to learn about analog to digital conversion and sampling. In many practical applications, the signals that we deal with are analog in nature. However, most modern digital systems process information in digital form. Therefore, we need a technique to convert an analog signal into a digital signal. This conversion is performed using an analog to digital converter, commonly called as ADC. So in this lecture, we will focus mainly on ADC and the sampling process. Most signals in the real world are analog signals. For example, speech signals, biological signals, seismic signals, radar signals, and sonar signals. So these are all examples of analog signals. An ADC is used when we want to process these analog signals using digital techniques. The basic conversion process consists of three important steps: sampling, quantization, and coding. First, the continuous time analog signal is sampled at discrete time intervals. Next, the sampled amplitudes are quantized into a finite number of levels. Finally, each quantized level is represented using binary code. So, the overall process can be remembered as analog signal, sampling, quantization, coding, finally digital signal. Let us understand this process using the diagram shown on this slide. Initially, we have an analog signal represented as x of t. The analog signal is continuous both in time and amplitude. After sampling, we obtain a discrete time signal represented by samples such as x of n. At this stage, the time variable becomes discrete, but the amplitude can still have continuous values. The next step is quantization. During quantization, each sample is assigned to one of a finite number of amplitude levels. The output is therefore called a quantized signal. Finally, coding assigns a binary number to every quantization level. The result is a digital signal represented using binary values such as zeros and ones. Therefore, these three stages together convert an analog signal into a form suitable for digital processing. Now let us focus on the first stage, which is sampling. Sampling means taking the value of an analog signal at regular intervals of time. If the sampling period is represented by capital T, then the samples are taken at 0, t, 2t, 3t, and so on. The sampled signal can be represented as x of n equal to xa of n capital T. Here x of n represents the discrete time signal and xa of t represents the original analog signal. The sampling rate is represented by Fs and the sampling period is represented by T. So the relationship between them is Fs equal to 1 by T. So if the sampling period decreases, the sampling rate increases. Similarly, if the sampling period increases, the sampling rate decreases. Look at the waveform shown on this slide. The continuous analog waveform is represented first. The sampler takes measurements at regular intervals. Each measurement gives us one sample of the original signal. If we take more samples per second, we obtain a more detailed representation of the original waveform. If we take fewer samples, some information about the waveform may be lost. So therefore, selecting an appropriate sampling rate is very important in an ADC system. So the objective of this system is to obtain sufficient samples so that the original analog signal can be represented and subsequently reconstructed accurately. Now let us look at the relationship among different frequency variables. For a continuous time signal, frequency can be represented in hertz or in radians per second. So the relationship is omega equals to pi f. Here f represents frequency in hertz and omega represents angular frequency in radians per second. For a discrete time signal, we can also represent frequency in cycles per sample or radians per sample. The slide shows the relationship between these frequency representations. Understanding these relationships becomes important when we analyze sampled signals and their spectra. So the next concept is ideal sampling. In ideal sampling, samples are obtained from the continuous time signal at equally spaced time intervals. The sampling operation can be visualized as taking instantaneous values of the analog waveform. So the important point is that sampling converts a continuous time signal into a discrete time signal. However, simply taking samples is not enough. The sampling frequency must be selected properly. If the sampling rate is too low compared with the highest frequency present in the analog signal, the original signal may not be recovered correctly. So this leads us to the sampling theorem. So this is what we have discussed. So now we'll move to the sampling theorem. This slide gives the important condition for exact recovery of a band limited analog signal. If the highest frequency contained in the analog signal is f max and the signal is sampled at the rate of fs, then the sampling rate should be greater than twice the highest frequency. Therefore, fs should be greater than 2 f max. This is the fundamental condition associated with sampling theorem. So this, in simple terms, the sampling frequency should be at least twice the highest frequency component of the signal to avoid loss of information during sampling. For example, if the highest frequency in a signal is 5 kHz, then the sampling frequency should be greater than 10 kHz. This condition is extremely important in digital signal processing and communication systems. So you can see the different examples for sampling rate. So we'll discuss in detail about quantization in the next lecture. So we'll summarize today's lecture on ADC, which converts analog to digital signal. So there are three major stages: sampling, quantization, and coding. So in this lecture we have concentrated on sampling. In the upcoming lecture we will concentrate on quantization and coding. So thank you for watching this lecture.